Okay, welcome back to Special Topics of Semiconductor Technology. Today we'll continue in Chapter 3. The new sections will discuss something about the so-called basic devices. These devices including resistor, capacitor, diode, bipolar transistor, and MOS transistor. These are all those basic devices that can be included in a circuit design. And in this chapter, we'll discuss in details how to build a resistor or a capacitor on top of silicon wafer. First, let's look at the resistor. We used to use a line of resistor to describe its geometry, with length L, width W, and its height H. And also we use symbol ρ representing the resistivity of these specific materials. In this geometry, the R is the resistance for this material, and ρ is the resistivities. W, H, and L are the conducting line width, height, and length for these materials. And as you can see that this is the geometry factor will affect the degree of resistance. So the longer the conducting wire, the higher the resistance. The larger the cross-section area, W times H here, then you have a lower resistance. And you can simulate a resistance on top of a wafer by design an area where you can dope with N-type or P-type elements into this area with certain depths. Within this area, from point A to point B, the conductivity is controlled by the concentration of the dopant that you introduced, either boron, arsenic, or phosphorus. The higher the concentration, the better the conductivity, the lower the resistance. And these we call sheet resistance. Okay, sheet resistor for a semiconductor fabrication process. So now you know how to simulate a physical resistors in a circuit design onto a silicon wafer by way of defining an area with a certain depth of dopant. By controlling the concentration of the dopant, you're controlling the concentration of the charge carrier. The more the charge carrier, the higher the conductivity, the lower the resistance. This is the first device we call resistors. So we know that resistors are made by doped silicon or polycrystalline silicon on IC chip. A lot of situation that you can use polycrystalline silicon instead of single crystal silicon to build resistors, but the way the charge carrier carry the signal is different. Okay, and the single crystal silicon is semiconductor materials. Polycrystalline silicon, polysilicon, is a polycrystalline material. This is not a semiconductor materials. Okay, this is not semiconductor material. A polycrystalline materials, you have a lot of grain boundary on your grain. For a signal to passing through, basically you also need to dope with phosphorus and boron, etc. This is polycrystalline silicon. And you need to dope, say, phosphorus ion. And those phosphorus ions will travel from point to another point along the grain boundary. So that will travel along the grain boundary. This is so-called grain boundary diffusion. Okay, so you actually traveling along grain boundary. For charge carrier, travel along grain boundary is fast. This is so-called grain boundary diffusion. It's a fast process. So you can use charge carrier by way of traveling along grain boundary to carry the signal. So polycrystalline silicon can be used as a resistors. Okay, it depends upon the dopant concentration. Again, you control the resistor. The resistance is determined by the length, line width, line height, that is the cross-section area, and the dopant concentration. Okay, this is the resistor. This is the first device we introduced. Next, we'll discuss about the capacitors. Capacitor basically is one of the most important components in IC chip, especially for memory chips. The capacitor can hold charge carrier. In the way of the computing, you can actually store your data inside a capacitor. That means you store charge carrier. Basically, a capacitor is a material with two electrodes separating by a insulator in between. Okay, an electrode on both ends, and you have insulating material in between, and this kind of geometry structure we call capacitor, and you can store charge carrier in this area, and this structure we call capacitor, and this is the symbol notation in your electronic design. The capacitance of a capacitor is equal to K times another term. Look at this term, dHL. H is the height of the electrode, L is the width, so HL is the area of the electrode. So this is area. And this is distance in between the gap. In between. The capacitance equal to the K times the geometry factor HL divided by D. So you can see as area increase, your capacitance increase. That means if you have a larger structure, then you can hold up more charge carrier. And if you can reduce the gap between the two electrodes, also you can increase the capacitance of the capacitors. Well, the constant K here is called dielectric constant. Different material has different degree of dielectric constant. Higher number of dielectric materials, or high K dielectric material, or sometimes we say low K dielectric materials. During the development of the IC fabrication technology, both high K dielectric material and low K dielectric material are constantly need to be developed according to your technologies, but both has different functions. So the capacitor here is the material which can store charge carrier. It's a device to store charge carrier, either electron or hole, positive or negative charge carrier. Okay, it can be used as a memory device such as DRAM. Actually, this is a charge carrier holding device. So you can read and write. When you write data, you actually store those charge carrier, and you delete the data, you release the charge carrier out of the capacitors. So you can write and delete, store and drain the charge carrier, and that is a basic function of a DRAM, a memory. And that write and delete is controlled by a transistor, So you can have full of charge particle and drain charge particle. So that would be 1 and 0 for binary systems. For the developing of capacitor, there's a challenge here. First, when you reduce the capacitor size, well, try to keep the capacitance. Let's look back over here. This is the size of your capacitor, the geometry factor. This is the area again. The larger the capacitor, you can hold up more charge carrier here. So you came up with a large cross-section area. You might get higher capacitance, and you reduce the gap in between two electrodes. But for the technology development, it looks like we are going to build a capacitors as small as possible. So when you reduce the geometry factor here, that means your capacitance also try to reduce. if you try to keep up with the capacitance at high volume, then you need to have a high K dielectric materials. So you need to develop in high K dielectric materials while reducing the size of your geometry, so it can hold up the capacitance of that capacitors. So that's why you need to develop in high K dielectric materials to keep up the capacitance while reducing the capacitor size. Okay, this again, you need to develop in high K dielectric material because it is used as a charge storage device. And this is capacitors. Over here shows you different kind of design of capacitors. First, this is parallel size. This is parallel pair. This is polycrystalline silicon, and this is single crystal silicon. And in between you have oxide. Normally this oxide is silicon dioxide. Silicon dioxide is a very good insulating materials used in semiconductor technology. So you have two electrodes basically, and there's oxide in between, from a parallel plate type capacitor, and this is called stacked. Due to the geometry of the silicon wafer, okay, the silicon wafer, the area of the size of silicon wafer has a limited size. So sometimes you came up with different design, try to hold up higher capacitance using different patterns of the capacitors. And this another one for the capacitor design. And the other one is called deep trench capacitor. Actually, this is a single crystal silicon. Okay, this will be, you will say, this is the width, the thickness of your single crystal silicon. And you came up from the surface, use a deep trench, came up with a deep trench here. Came up with a deep trench here, and then this will be single crystal silicon, so it's a heavily doped single crystal silicon, and this is dielectric layer, the insulating, the great area is insulating layer, and then again you deposit polycrystalline silicon here. After the polycrystalline silicon deposit, you need to introduce into the polycrystalline grain boundary with maybe phosphorus or arsen, okay, or arsenic iron. So those iron can travel along grain boundary and become an electrode, and this can take up a small footprint on the wafer size. So this is a wafer. You basically can going deep into the silicon wafer and form a so-called deep trench type capacitors. For the high K dielectric material, we mentioned that you developing high K dielectric material is because when you're reducing the size of capacitors, but try to keep up with the capacitance, so you need to developing high K dielectric material. For a dielectric material, basically it's an insulator. So sometimes it acts as a function, just an insulator, not a charge storage device. The geometry here, it looks like a capacitor. You have a conducting wire, another conducting wire. In between, you have insulating materials. This is insulator. So it looks like you have one electrode, the other electrode, and in between has a insulating material. It looks like a capacitor. But here, the purpose of this geometry, this design, is basically two conducting wire need to be separated by dielectric materials, insulator. So in this case, the signal coming from this side coming through this direction. Because of the geometry like this, you will come up with the so-called RC delay. The signal you send off will wait a time delay. When the first signal came out, a delay is required for second signal being sent out from the system. So in that case, the time delay equal to so-called R times C, RC. We call RC delay, because the signal between the consecutive signal, the time delay between the consecutive signal will be the resistance of the conducting wire times the capacitance of the insulator materials here. So you try to have a fast operation of ICs, sending out signal at high velocity, higher speed, higher frequency. Then you need to have time delay R times C as small as possible. So right now, the time delay equal to R times C. What can you do to reduce T? What can you do to reduce T? That means reduce it first. Resistance. Can you change the resistance or lower the resistance of the conducting wire? Yes. You can use aluminum in the past as a conducting wire and change it to copper right now as a conducting wire. You actually reducing the resistance, so you can come up with a lower time delay. But it doesn't look like in the future you're going to change copper maybe into silver, okay, change it into silver or gold, because the cost is much higher than the performance gain by changing from copper to silver. In that case, it looks like the resistance will going to be fixed in the future. So when you try to reduce time, the time delay, the T, The only thing is try to reduce C, the capacitance. So again, going back to here, how do you reduce the capacitance? Your geometry factor could be fixed in the future. Further design, reducing the capacitance require a lower K dielectric material. So not only you developing high K dielectric material for charge storage device, you also need to developing low K dielectric material to reducing the time delay equal to resistance of the conducting wire times capacitance of the insulator. So this is where you developing low K dielectric materials. So the capacitance here, that means the dielectric material here, is not used for charge storage device, but used as an insulator between two conducting wire. So that is where the low K dielectric material plays an important role here. Okay, in this section we discuss the basic device of resistor and capacitors. Okay, and showed you how to simulate a physical resistor by way of dopant introduction into the silicon wafer in a specific area with specific depths. We call sheet resistance. That means sheet resistors. Okay, the higher the dopant concentration, the higher the conductivity, so which will have a smaller resistance. For a capacitor, basically you constantly developing high K dielectric material and low K dielectric materials, where the high K dielectric material is used for a charge storage device. When the geometry reduces in size and you try to keep up with capacity to hold up the charge carrier, you need to have a high K dielectric materials. In the other hand, when the dielectric materials is not used for a charge storage device, it basically serves just as an insulator in between two wires. In that case, a term called time delay, RC time delay, will occur for a consecutive signal. When you're sending out, there's an interval between two signals, and that is the RC delay, the time required for a consecutive signal to be sending out. So the T equal to R times C. R is the resistance of the conducting wire. In the past, we used aluminum as the conducting wire. When you try to reduce the resistance, you can change your aluminum to copper, maybe into silver. But when you change into silver, the decrease of the resistance doesn't have the same effect to reduce the cost. Okay, so that means it's not cost effective. So once you have the resistance fixed, when you're using copper as the conducting wire, the only way to reducing the time delay is to reduce the capacitance of the insulator. That means you need to developing low K dielectric materials. So why you need to developing high K dielectric materials and low K dielectric materials? There's a different function here. Okay, this will be the section we discuss the basic device of resistors and capacitors.